require some basics of definite integrals. So I thought might as well get you introduced to the function there. Essentially, when I have dx, which is some phi x plus c, then what this means is that phi dashed x must be c, right? Phi dashed x must be fx. That's what it means. This is the primitive and fx is its derivative. This is the primitive and fx is its derivative. Now, integral a to b fx dx is essentially the change in phi x when x changes from a to b, which is like phi b minus phi a. And the geometric meaning of integral fx dx a to b, and I'm not going to spend time on it right now, I'm going to come back to it. The geometric meaning of y equal to fx dx, integral fx dx a to b, is the area under the graph of y equal to fx when x changes from a to b. This area is what is implied. Integral fx dx a to b means the area under the graph of y equal to fx when x changes from a to b. And by the way, you know, although it sounds so simple, this theorem integral fx dx a to b is phi b minus phi a is actually Newton-Leibniz theorem. Now, integral dx a to b. See, this x is only a temporary variable. It gets dissolved the moment you apply the limits, right? So it does not matter whether it's x or it's y or it's z or it's t or it's anything else, right? Which means instead of this x, if you had like a t, then also it's going to be the same, a to b. Or if you had a z, then also it does not matter. Yes or no? So this is only a temporary variable and it goes into oblivion the moment you supply to the integral, right? Also, easy to see, area integral fx dx a to b is negative of integral fx dx b to a. Because one would be phi b minus phi a, the other one would be phi a minus phi b. So integral a to b dx is negative of integral fx dx b to a. Right? Now, some very general, if there is a function y equal to fx, which is greater than or equal to 0, then the graph of this function would be strictly above the x-axis. Area from a to b, the area from a to b would be positive, Area from a to b would be, it means if fx is greater than or equal to 0, integral fx dx a to b would be greater than or equal to 0. Similarly, if I have a function y equal to fx, which in a given interval a to b, this is the graph of y equal to fx, in a given interval a to b, it's higher than the graph of y equal to gx. That means, for all x belonging to a to b, if we have fx larger than or equal to gx, if for all x belonging to a to b, if f of x is larger than or equal to gx, then the area under fx would be larger than the area under gx from a to b. So, fx greater than or equal to gx in a given interval a to b would cause integral fx dx a to b to be larger than integral gx dx a to b? Yes or no? Right? There are times when you can't integrate a certain function, yet the area under the curve exists. Yet the area under the curve exists, right? Can't find a primitive to a certain function. Say, the graph of y is e, say from 0 to 1. Say from 0 to y is e power x squared is this. Right? This is the graph of y is e power x squared when x changes from 0 to 1. Now, integral e power x squared dx, x changes from 0 to 1. Is this area? Is this area? Yes or no? Is this area? But you can't find a primitive to e power x squared. That means you can't find a function which upon differentiation is going to give you e power x squared. In engineering situations, you still need an approximation to this area. Even if you can't find this exact, you need an approximation to this area, right? It would have been so simple if we had a primitive to this function and we could readily Newton-Leibniz law to find the area. In this case, what? Realize that the graph of in the interval 0 to 1, in the interval 0 to 1, x squared would be less than x, yes or no? X squared would be less than x. So can I say that in this interval, e power x squared would be less than e power x? E power x squared would be less than e power x. So which means the graph of e power x is higher than the graph of e power x squared. Although at x equal to 1, they assume the same value. At x equal to 0, also they assume the same value. This is the graph of y is e power x. This is the graph of y is e power x squared. Right? So, what we really know out of this is that if e power x squared less than e power x, can I conclude that integral e power x squared dx, x runs from 0 to 1, is less than integral e power x dx, x runs from 0 to 1? Yes or no? Right? Also, guys, that this is 1, this is 1, at x equal to 0, e power x squared is 1. So, in the interval 0 to 1, the area of this rectangle is 1 unit. The area of this shaded rectangle is 1 unit. Now, I can also say that e power x squared is greater than 1, less than e power x. Can I say this? Can I say this in this entire interval 0 to 1, e power x squared less than e power x, greater than 1? And based on this, I say e power x squared dx 0 to 1 greater than 1 into dx, x changes from 0 to 1, less than integral e power x dx, x changes from 0 to 1. And this is the area under the graph of e power x squared, this is the area under the graph of e power x squared. Means the required area A, which is this, has to be less than this is like e minus 1, has to be less than e minus 1, but is greater than 1. Greater than 1. So we get an idea of the area then. We get an idea of the area, even if the exact area is not obtainable, an idea of the area could be obtained. We have some feel for what the area under the graph could be. Right? Now, Say if we had a function of this kind to integrate. Four minus square minus x cubed, x runs to 1. Right? Can't integrate this function. We can't find a primitive to this function. We can't find this definite integral definitely. But then we can approximate it. We can find the range over which it lies. We can find the range over which this lies. How do we do that? Realize that 4 minus x square in the interval 0 to 1, right? X lies in the interval 0 to 1. X belongs to 0 to 1. In the interval 0 to 1, do you realize that x cube would be less than x squared? X cube would be less than x squared, yes or no? 4 minus x squared minus x cube in the first place is less than 4 minus x squared. One thing, it's less than 4 minus x squared. 4 minus x squared minus x cube would be less than 4 minus x squared, yes or no? Right? But would be greater than 4 minus x squared minus x squared, yes or no? Because realize that minus x cubed will be greater than minus x squared. Minus x cubed will be greater than minus x squared, yes or no? This minus x cubed is greater than this minus x squared. So this expression is larger than this expression when x belongs to 0 to 1, yes or no? Right? Now when I take the reciprocal of the entire thing, the direction of the inequality will change throughout. The direction of the inequalities will change throughout. So 1 by 4 minus x squared minus x cubed would be less than 1 by 4 minus 2x squared. 1 by 4 minus x squared minus x cubed would be less than 1 by this and would be greater than 1 by 4 minus x squared. How about it? Yes or no? And therefore, if I take the square root, 1 by root 4 minus 2x squared is greater than 1 by root 4 minus x squared minus x cubed, which would be greater than 1 by root 4 minus x squared. Yes or no? Now, if this function is larger than this function, in the interval 0 to 1, then integral of this from 0 to 1 would be larger than the integral of this from 0 to 1, would be larger than the integral of this from 0 to 1, yes or no? So, which means integral dx by root 4 minus x squared minus x cubed 0 to 1 is less than integral dx by root 4 minus 2x squared. X changes from 0 to 1 is larger than integral dx by root 4 minus 2x squared. 4 minus x squared. X changes from 0 to 1, yes or no? Now, this would be sine inverse x by 2. X changes from 0 to 1, yes or no? This is easy to integrate. This is going to be sine inverse x by 2. X runs from 0 to 1. How about it? When x is 1, this is sine inverse half, which is pi by 6. At x equal to 0, it will be sine inverse 0, which will be 0. So this turns out to be pi by 6. Yes or no? As far as this part is concerned, I can take 2 common from this. So when I take 2 common from this, 1 by root 2, integral 0 to 1 dx by root 2 minus x squared. So this would be like 1 by root 2 sine inverse x by root 2. X changes from 0 to 1. So this becomes pi by 4. So pi by 4 root 2, this becomes pi by 4 root 2, yes or no? That means this integral is less than pi by 4 root 2 and is greater than pi by 6. So we can approximate, even if we can't find the exact integral, we can approximate the integral, yes or no? Right? Are you there with me? Right? If I have a function, say which is monotonically in an have a function which is monotonically increasing in interval a to b, then this is fa, this is fb. This is fa, this is fb. This is a function which is monotonically increasing in the interval a to b, right? So say for any x belonging to a to b, for any x a to b, f of x would be larger than or equal to fa and less than or equal to fb. Now I can afford to take the integral of all of these from x equal to b. So yes or no? That means now this is very clearly fa into b minus a. Fa will come out, fa into b minus a, yes or no? And this is going to be fb into b minus a. This is going to be fb into b minus a. Now suppose a function is not monotonic in a given interval. Then it will have a largest value and a smallest value in that interval, which could happen anywhere, right? Suppose a function is not monotonic in an interval, it will still have a largest value capital M and a smallest value small m in that interval. So capital M is the largest value of the function in a given interval, greatest value of a function in an interval, and small m is the smallest value of the function in the interval, least value of the function in the interval. Then again I can write throughout integral fx dx a to b less than or equal to integral m dx a to b or equal to integral small m dx a to b, right? So if capital these values of a function in an interval a to b, then this will always be less than or equal to m into b minus a and would be greater than or equal to small m into b minus a, where small m and capital M are the smallest and the largest values of the function in the interval a to b. Integration, realize, is a process of summation. Integration is a process of summation. In a very general sense, if x1, x2, x3 are a set of real numbers, then the modulus of the sum would be less than or equal to sum of the moduli. Modulus of the sum is less than or equal to the sum of the moduli. Now, extending this concept to integration, if I had modulus of integral fx dx a to b, modulus of integral fx dx e, which is modulus of a sum, this will always be less than or equal to sum. This is the integral is sum of the moduli. Moduli are the fx's. For various values of x, you have various mod of fx's, right? So this is another important principle. Modulus of the sum less than or equal to the sum of the moduli. This is integral is sum of the moduli, right? Yes? Got me now? Suppose fx and gx are any two functions. Fx and gx are just any two functions. Then say fx minus lambda gx whole square for any given x will be greater than or equal to 0. Can this be said? Can this be said? For any given x, fx minus lambda gx whole square will always be greater than or equal to 0. Which means lambda squared g squared x minus 2 lambda fx gx plus f squared x will always be greater than or equal to 0. Yes or no? Where lambda is a parameter independent of x. Let's say lambda is independent of x. Now if this function is greater than or equal to 0, its integral from a to b will always be greater than or equal to 0. Right? Its integral from a to b is like lambda squared integral g squared x dx a to b minus 2 lambda integral fx gx dx a to b plus integral f squared x dx a to b will always be greater than or equal to 0. Yes or no? Right? This is a quadratic in lambda. It's a quadratic in lambda. In terms, this quadratic in lambda is an upward opening parabola because this will always be greater than or equal to 0. It's an upward opening parabola. And if this is greater than or equal to 0, its discriminant must be less than or equal to 0. Its discriminant must be less than or equal to 0. Discriminant means b squared minus 4ac, which will clearly give you integral fx gx dx a to b whole square less than or equal to integral g squared x into f squared x dx, x changes from a to b. Yes or no? This is an important inequality in definite integrals. This inequality is called Cauchy-Bunyakovsky inequality. These Russians have an uncanny knack of interest everywhere. I mean, I guess, this is adapted out of Cauchy, applied to integration. Gentleman Bunyakovsky just did some little bit of fundamentally Cauchy, I'm also one of the pioneers. So Cauchy-Bonnier-Woski inequality. Cauchy-Bonnier-Woski inequality. Useful inequality. Again, very good towards estimation of, like all along I've been doing estimations, right? This again would be a tool towards estimation of non-integrable functions, right? So far so good, right? Now, there could be a function which could be discontinuous, let's say at a certain point C1. C. Could be discontinuous at a certain point C in the meet of AB. Now if I seek integral fx dx a to b, then what I do, I break this interval a to b at a point C. I calculate this integral from a to c and then from c to b, because from a to c the behavior is of one kind, from c to b the behavior is of another kind. And this could be written as integral a to b, a to c, fx dx plus c to b, fx dx. If there are a number of such points, let's say C1, C2, Cn between a and b, where the function has exhibited a change of behavior, and I have to calculate integral fx dx from a to b, then what I do is integral fx dx from a to b, and there is change of behavior at C1, C2, Cn. What I do is I calculate this from a to C1 and then from C1 to C2, C2 to C3, and then Cn to b. That's what I do. So this could be written as a to C1 fx dx plus C1 to C2 fx dx, and going this way, integral Cn to b fx dx. Oh no, right. For example, say I have a function y equal to fx, which is x plus 1 for x less than or equal to 3, and is 2x minus 1 for x greater than 3, for x greater than 3. Okay. And I want to be able to calculate integral fx dx from 2 to 4, say, from 2 to 4. Now, 2 to 3, the behavior is like this, and then 3 to 4, the behavior is like this. So, from 2 to 3, I will use this as the description. From 3 to 4, I will use this as the description. Yes or no? So, if I have to calculate this integral, then what I do is, from 2 to 3, fx goes like x plus 1, fx goes like x plus 1. And then from 2 to 4, fx goes like 2x minus 1. Right? It need not be discontinuous at x equal to 3. Even if there is a change of behavior, you will have to relocate the function. But calculate integral mod of x minus 5 dx 2 to 6 say. Then what I do is at t 2 to 5 and then 5 to 6. Now, this is less than 5. Mod x minus 5 is going to be 5 minus x. Is going to be 5 minus x because 5 minus x will be positive. And then 5 onwards, x greater than 5, so mod x minus 5 would be x minus 5. Yes or no? So in this case, see, mod x minus 5 is not continuous at x equal to 5. But there is a change of behavior at x equal to 5. Right? But it's not discontinuous. Yet, you are advised to do this. Right? Now suppose I had integral box x dx, x changes from 0 to 3, x changes from 0 to 3. Then again, you will take intervals like 0 to 1, 1 to 2 and 2 to 3. In the interval 0 to 1, box x is 0. Yes or no? Then 1 to 2. When x changes from 1 to 2, box x is 1. And then 2 to 3. When x changes from 2 to 3, box x is 2. Yes or no? Suppose I had box of root x. X changes from 0 to 6.5. X changes from 0 to 6.5. So, I would cause x to change from 0 squared to 1 squared. 1 squared to 2 squared. 2 squared to 6.5. You know what I'm saying? I would choose the following. X changes from 0 to 1. So, root x changes from 0 to 1. And box okay. Then, in fact, just to be technically correct, 1 squared to 2 squared changes from 1 squared to 2 squared. Root x changes from 1 to 2. Root x changes from 1 to 2. So, box of root x will be 1. Now, x changes from 2 squared to 6.5. When x runs from 2 squared to this is less than 3 squared. This is less than 3 squared. Yes or no? Root x runs from 2 to 3. Let's see. Root x runs from 2 to 3. Box of root x will then be 2. Simple, right? All of you got it? Now, let me look at some more properties of definite integrals. Some more properties of definite. Integral fx dx. X changes from a to b. Integral fx dx, x changes from a to b is integral f of, this is the most popular property of definite integrals. Integral fx dx, x changes from a to b is integral f of a plus b minus x, x changes from a to b. Now, the way to deal with it, look at the right hand side. Look at this right hand side. Call a plus b minus x as some z, Right? So, I'll go from the x domain to the z domain, right? Very clearly then, dx would be minus dz. Dx then would be minus dz, yes. So now this is fz, dx is dz with a minus sign. Now look at the limits. Now the limits would have to be in terms of z. When x is a, what is z? When x is b, what is z? The new variable is z. So when x is a, z is b. When x is b, z is a. In the z domain, this is what happens. Yes or no? Now I can assimilate the minus sign to swap these limits. I can interchange the limits by using the minus sign. So I assimilate the minus sign. fz dz. Z changes from a to b. The minus then gets absorbed. Now, whether this is z, or this is t, or this is x, or this is London, or this is Hong Kong, or this is Paris, it does not matter, right? So might as well call it x now. Might as well call it x now. So this then becomes integral fx dx, x runs from a to b. Yes or no? Right? So very important property, very important property. You know what I'm saying? A corollary of this property, 0 to a fx dx, integral 0 to a f of x dx. See, in this case a is 0 and b is 1. So this I could write as integral f of 0 plus a minus x dx. Yes or no? A to b is going to be a plus b minus x. A plus b minus x. Yes or no? So this then turns out to be integral 0 to a f of a minus x, which is just a consequence of this general property. Right? This is the most commonly used property, most important property of definite integrals. Now, say if I had integral 0 to pi by 2 g of cos x by g of sin x plus g of cos x. Suppose I had something like this. The same as replacing x by 90 minus x. So this integral I is the same as g of x replaced by 90 minus x now. So g of sin x divided by g cos x plus g sin x. X changes from 0 to pi by 2. Yes or no? So, if this equals this, then each would be half their sum, each would be half their sum. If A equals B, then each would be A plus B by 2. Right? So then each would be equal to half of pi by 2. G cos x plus G sin x divided by G sin x plus G cos x dx, which would be pi by 4, as you can see. So now instead of sec and sin x, if you had tan x and cot x, you will still get pi by 4. If you had sec x and cosec x, you will still get pi by 4 and so on. Right? 0 to pi x by 1 plus sin x. 0 to pi x by 1 plus sin x. Now, x can be replaced by pi minus x. X could be replaced by pi minus x. So this is going to be integral pi minus x dx by 1 plus sin x. X changes from 0 to pi. Yes or no? Each of this is I. If this equals this, then each would be half their sum. Each would be half their sum. Yes or no? So then half their sum means X will get cancelled. So it's going to become pi by 2 half their sum integral dx by 1 plus sin x. X changes from 0 to pi. See, x replaced by pi minus x will still give me sin x. Right? Easy to integrate. How do you integrate this? How do you integrate this? Louder. No, you're terrible. I mean, this is pi by 2. 1 minus sin x by cos squared x. Multiply by 1 minus sin x both numerator and denominator. So sec squared x minus sec x tan x. Yes or no? This will be sec squared x minus sec x tan x. Sec squared x would be tan x. Sec x tan x would be sec x. Yes or no? That's what you do. Now suppose I have integral pi by 6 to pi by 3, 1 by 1 plus root tan x dx. Pi by 6 to pi by 3, 1 by 1 plus root tan x dx, right? To be f of a plus b minus x. Realize that in this case a plus b is 90. Pi by 6 plus pi by 3 is pi by 2, right? But pi by 2 minus x. A plus b minus x, that property. So this could be written as integral pi by 6 to pi by 3 gx by 1 plus root tan 90 minus x, that is cot x, right? Which could be written as pi by 6 to pi by 3 root tan x by root tan x plus cot x. Tan x plus 1, sorry, root tan x plus 1. Yes or no? Isn't it? So if this equals this, then each would be half their sum. If this equals this, they have the same denominator. Right? Then each would be half their sum. What's their sum? Sum of this and this is 1. Right? So if this equals this, then each equal to half their sum. Half their sum is 1. X changes from pi by 6 to pi by 3. Yes or no? Half their sum. Sum is 1. This plus this. Yes or no? So which is simply half of pi by 3 minus pi by 6. Pi by 12. Right? Zero to pi dx by 1 plus a power cos x. Let's say a is a positive number. A power cos x. Very simply, this could be written as 0 to pi dx by 1 plus, replace x by 19 pi minus x. So minus cos x. So 1 plus a power minus cos x. How about it? Right? Which then is evidently 0 to pi a power cos x dx by 1 plus a power cos x. Yes or no? If this equals this, then each would be half their sum. Their sum is 1, as you can see. So it's simply going to be half integral dx 0 to pi, which would be pi by 2, which would be pi by 2. Yes or no? Okay. Pretty useful property. Now, integral minus a to plus a fx dx. Integral minus a to plus a f of x dx is 0 to a f of x plus f of minus x. F of x plus f of minus x. Very clearly, this minus a to a could be written as minus a to 0 f of x dx plus 0 to a f of x dx. Yes or no? This minus a to a could have been written as minus a to 0 and then 0 to a. Now I don't touch this because this matches with this. I just need to tinker around with this. What I do is, in this case, I need a here. I don't need minus a. So I create a transformation. I create a new variable t which is negative of x. So that when x is minus a, t becomes a. I need a here for some reason, right? So when x is minus a, t is a. When x is 0, t is 0. Do you also realize that dx is minus dt here? Dx is minus dt here. So replace this dx by minus dt. This is f of minus t. This is f of minus t. Now I could use this minus sign to swap the limits of integration. I could use the minus sign to interchange the limits of integration, right? So I could write this as 0 to a f of minus t dt. Why t? London, Paris or x, right? It does not matter. So now might as well call it f of minus x dx. Yes or no? Keshav. So very clearly, this expression minus a to 0, like 0 to a f of minus x dx, which then brings us directly to this result. Very useful result. Almost as useful as the previous result. Very clear. F. You know what even functions, odd functions are? Even functions are those for which f of minus x is fx. Even functions will have f of minus x is fx. These are even functions. Odd functions are those in which f of minus x would be minus fx. These are odd functions. Now if I have an odd function, then f minus x will be minus fx and it will become 0, right? This will be 0 if f is odd. If fx is odd, this will become 0. Minus a to a, fx dx will become 0 if f is an odd function of x and would be 2 times 0 to a fx dx if f is even. Very clearly, if f is even, f minus x will be equal to x. F minus x will be equal to x. Can I wipe this off? You have the sheet on you, right? Let me illustrate some of these in the sheet itself. Look at problem number 19 or look at problem number 17. Look at problem number 17. Log half to log 2 sine of e power x minus 1 by e power x plus 1 dx. Now half is like minus log 2. Log half is like minus log 2. Now look at this function, look at this. So it's like minus a to plus a fx dx. Fx is sine e power x minus 1 by e power x plus 1. F minus x is sine e power minus x minus 1 divided by e power minus x plus 1. Yes or no? Right? Which is like sine of 1 minus e power x by 1 plus e power x. Clear? Which is minus sine e power x minus 1 by e power x plus 1. Yes or no? In which case f minus x turns out to be minus fx. Minus sine this, minus sine this. So f minus x turns out to be minus fx. So what is fx? Odd. Fx is odd. And then minus a to a, fx dx is going to be 0, is going to be 0 because f is an odd function. F is an odd function. Let me take a few more from the sheet. Look at problem 14. Minus a to a fx dx. Let's check for fx whether it's even or odd. Now, fx is ln x plus root x square plus 1. F minus x is ln minus x plus root x squared plus 1. That's f minus x, yes or no? Let me add the two. Fx plus f minus x. ln a plus ln b is going to be ln ab, is going to be ln ab, ln a is going to be ln this plus this into this plus this minus this into this plus this would be x square plus 1 minus x square. So that's going to be ln 1 which is 0, yes or no? That means fx plus f of minus x is 0, which means f of minus x is minus fx, so f must be an odd function of x. If fx is an odd function of x, this integral must be 0. Right? Number 15. Fx is e power x plus 1 by e power x minus 1 and integral 0 to 1 e power x plus 1 by e power x minus 1 dx is lambda into x dx is lambda, right? We need to find minus 1 to 1 TFT. Hey, this is like TFT only, right? This is like TFT only. Do you realize that fx is x into fx is this only. So x fx, this function x fx, call it phi x, is x into e power x plus 1 by e power x minus 1. That's phi x, that's phi x. What's minus x? minus x into e power minus x plus 1 divided by e power minus x minus 1, yes or no? Which you realize is going to be x into e power x plus 1 divided by e power x minus 1 when I use the minus sign. So 5 minus x is the same as 5x. 5 minus x is the same as 5x. So 5 must be an even function. 5 must be an even function. Yes or no? 5 then is an even function of x. So this is like 5t. This is like 5t. TFT is 5t. It's an even function. So do you realize that this must be twice 0 to 1 TFT dt? This is twice 0 to 1 TFT dt, yes or no? Huh? But TFT dt or x fx dx is going to be the same, right? Hey, but do you realize that this is x fx dx 0 to 1, that's lambda. That's lambda, so this must be twice lambda. This must be twice lambda. Right? Okay, so useful property, this one pretty useful. Now, another very useful property, 0 to 2a fx dx. Integral 0 to 2a fx dx. This is 0 to a f of x plus f of 2a minus x. Is 0 to a f of x plus f of 2a minus x. Now, this I write as 0 to a fx dx plus a to 2a fx dx. How about it? Now I don't touch this because this 0 to a fx dx is already prevalent here. I need to work around this. I need to work around this second integral. The first one matches with this. Yes or no? I just need to show that integral a to 2a fx dx is 0 to a f of 2a minus x. Then the problem will be solved. Okay. So let me just look at a to 2a separately. Let me call 2a minus x as some t. So that when x is a, t would be a. When x is 2a, t would be 0. A and 0 in my limits. Right? So when I do this very clearly, then dx would be minus dt. And x would be 2a minus t, x would be 2a minus t. This then dx with a minus dt, f with 2a minus t. When x is a, t is a. When x is 2a, t is 0. Right? What did I use this minus sign for? Swapping the limits. T or London or Paris or Hong Kong or X is going to be the same. So let's put X. Right? So this is the same as 0 to a f of 2a minus x dx. Does it make sense to all of you? Shall we proceed? Let me illustrate this. 0 to pi by 2 log sin x. Let me find out this integral. Zero to pi by 2 log sin x. Now 0 to pi by 2 log sin x is the same as 0 to pi by 2 log cos x. Replace x by 90 minus x, right? If A equals B, E should be half their sum. E should be half their sum. Sum means log sin x plus log cos x, which is log sin 2x by 2. Which is log sin 2x by 2, yes or no? Which is half of 0 to pi by 2 log sin 2x dx minus log 2 dx 0 to pi by 2. How about it? Yes or no? Which I could write as half of 0 to pi by 2 minus pi by 2 log 2, yes or no? Does it make sense? Okay. Now, just to create rule, this is half of 0 to pi by 2 log sin 2x dx minus pi by 4 log 2, right? That was the last statement that I wrote. That was the last statement that I wrote, yes or no? What's the problem? Right. Now I don't touch this. Resolve. I need to play around with this. So what I do is, first of all, instead of making 2x here, let me call 2x as some t. Let me call 2x as some t. As far as this part is concerned, let me call 2x as some t. T is some 2x. So that when x is 0, t is 0. When x is pi by 2, t would be pi. Right? A new variable is brought in, which is double the earlier variable. That means t would be twice this and twice this. So 0 to pi would be the new limits of integration. Also realize that dx would be half dt. Dx would be half dt. Yes or no? Right? Now what I do is, my problem is everything except that, it would have been really good if this was like a pi by 2 here. It would have been really good had it been a pi by 2 here, right? So what I do is, in any case, what stops me from writing this as 0 to 2 times a, 2 times pi by 2? 0 to 2 times pi by 2, right? And the earlier result which I wrote was 0 to 2a fx dx is like 0 to a fx plus f of 2a minus x. Right? That was the result that I wrote. So this will be 1/4 of 0 to a. A is pi by 2. Log fx means log sin t plus f of 2a minus x, that means f of pi minus t, f of pi minus t. That means log of sine pi minus t would be log sine t itself, would be log sine t itself. Yes or no? This is ft plus f of 2a minus t, that means f of pi minus t. It should be log sine t itself. Got me? Which then, this is twice, so this is going to become half of 0 to pi by 2 log sine t dt minus pi by 4 log 2. Okay, do you realize that t or x does not matter? So call it x. But then this is I. So we have I equal to I by 2 minus pi by 4 log 2. So I then becomes minus pi by 2 log 2 is transposing. I then becomes minus pi by 2 log 2. I want you to remember this result. 0 to pi by 2 log sine x is minus pi by 2 log 2. Realize that when x runs from 0 to pi by 2, sine x is less than 1. Logarithm of a number less than 1 would be negative. So the graph of log sine x in the interval 0 to pi by 2 is below the x-axis. That's why you're getting a negative number out of it, minus pi by 2 log 2. You know what I'm saying, right? So far so good, right? No issues. Now, some periodic functions. Fx is periodic. And period. When I say t is its period, it does not necessarily mean t is the fundamental period. It could be a multiple of the fundamental period also. It does not matter. Whether t is the fundamental period or not, I can still say f of x will be f of x plus t. But t is just the periodicity, it is an integral multiple of the fundamental period. You know what I am saying? Then also this result will hold good. Now, very useful property. N is a natural number. N is a natural number. 0 to n times t fx dx is n times 0 to t fx dx. Very easy to see, really. Realize that the graph of fx, say, over one period is like this, 0 to t, and then t to t, it will be identical, and then 2t to 3t, it will be the same, going this way, and then eventually n minus 1t to nt will be like this. So what is this? This is the area from 0 to nt, and all these areas from 0 to t, t to 2t, 2t to 3t are identical. So this would be, this entire area under the graph would be n times the area from 0 to t. This is what the statement is. Yes or no? Very important property of definite integrals. 0 to n times t fx dx is n times 0 to t fx dx. Right? Let me also establish for academic interest this result independently. without using graphs, purely algebraically. Look, 0 fx dx is 0 to t fx dx, and from t to 2t fx dx, and then 2t to 3t, n minus 1t to nt fx dx. Right? 0 to t, t to 2t, and so on so forth. This, for convenience, we write as summation r minus 1t to rt fx dx. R runs from 1 to n. R runs from 1 to n. If you plug in r equal to 1, you will get this. If you plug in r equal to 2, you will get the second. If you plug in r equal to 3, you will get the third. Plug in r equal to n, you will get last integral. Yes or no? Right? Now, I attempt to produce a transformation here. The transformation is, in this integral, I say x minus r minus 1 into t as some z. So very clearly, dx will be the same as dz. Yes or no? Now when x is r minus 1 into t, z is 0. When x is rt, z is t. Yes or no? So the new limits of integration in terms of the new variable z would be 0 to t. So this whole thing is summation integral 0 to t f of z plus r minus 1 into t. Dx is the same as dz. R runs from 1 to n. Yes or no? Yes or no? R minus 1 into t is only an integral multiple of the fundamental period. F of z plus a multiple of the fundamental period would be the same as f of z. Will be the same as f of z. Yes or no? You know what I'm saying? This will be the same as f of z. So this is summation r equal to 1 to n integral f z dz 0 to n 0 to t. Hey, do you realize that this is summation of n identical integrals of this kind? N identical integrals of this kind? This is going to be n times 0 to t f z dz. Z or London or Patna or Paris does not matter. N times 0 to t fx dx. Got me? Another property for periodic functions. T is the period, a to a plus n times t, where n is an integer. This I claim will be the same for all a. This integral I claim will be the same for all a. That means it's going to be independent of a. That means I claim this integral will be independent of a. This I claim would be independent. Now, this is a very useful property, very useful property. Say integral fx dx is some phi x plus c, right? Which means phi dash x must be fx. Phi dash x must be fx. That's what it means. Clear? Now, integral a to a plus nt fx dx is going to be phi of a plus nt minus phi of a. Phi of nt minus phi of a. Leibniz theorem. We want to show that this expression does not have any a in it. This means it's independent of a. That's what we want to show. If an expression is independent of a, does not have any a in it, and if you differentiate it with respect to a, what should you get? 0. So let's check by differentiating this with respect to a. The right hand side with respect to a, if I get 0, then it's independent of a. Yes or no? So let me differentiate the right hand side with respect to a. This is evidently phi dash a plus nt minus phi dash a, yes or no? Hey, but phi dash x is fx, so phi dash a plus nt would be f of a plus nt, would be f of a plus nt minus f of a. Hey, but f of a plus nt is fa. Why? Because t is the period of fx, so f of a plus nt is the same as f of a, right? So this is f of a minus f of a, which is 0. That means it's independent of a. That means in this case, you can plug in a equal to London, Patna, Paris, Hong Kong, Switzerland, whatever you like. It's going to have the same value. Right? Got me? Very, very important result. Very important result. Integral fx dx a to a plus nt is independent of a. So if it's independent of a, it's going to give me the same value when I plug in a equal to 0 than any other value of a. So as a special case, if I plug in a equal to 0 here, as a special case, if I plug in a equal to 0 here, then this will be 0 to nt f of x dx. Hey, but 0 to nt fx dx is n times 0 to t fx dx. How about it? Can I write this off? M is an integer, n is an integer, t is the period of the function, t is the period of the function, is n minus m, 0 to t, fx t. Geometrically you can see that. Again, from algebra also I'll tell you how that happens. Say if I took x minus mt as some z, x minus mt as some z, right? Then this integral would become dx is the same as dz, and x is like z plus mt. When x is empty, z is 0. When x is empty, z is n minus m into t. Hey, but f of z plus mt is the same as f of z because t is the period of the function, right? Zero to integer times t would be integer times 0 to t. Integer times 0 to t f z is say or London or Patna or Paris or X. So might as well have X. Got it? Another property of periodic functions. A plus nt to b plus nt is a to b fx dx. What I do is, say I want to eliminate nt here, both from numerator and denominator, right? So if I took this x minus nt, if I subtract nt from these two x's, then nt gets obliterated, right? So x minus nt, let me take as some z. So that when x is this, z is a. When x is this, z is z. You know what I'm saying? So the new variable here is z, f of x. X I write as z plus nt. Dx is the same as dz. When x is this, z is a. When x is that, z is b. But f of nt is the same as f of z. Z or London or Patna or Paris or X going to be the same. Got me? Now, one extremely important result in definite integrals, extremely important result in definite integrals, which is differentiation under the integral sign. Differentiation under the integral sign. I have a function f depending on x and alpha. Alpha is a parameter. Alpha is a parameter. It's integrated with respect to x. It's integrated with respect to x. And the limits of integration are functions of alpha. The lower limit of integration a will depend on alpha. The upper limit of integration b will depend on alpha. So when you integrate it with respect to x, you get a function of x. But the moment you supply the limits a of alpha and b is a function of alpha, the whole thing becomes a function of alpha. This eventually is a function of alpha when you supply the limits, when you integrate with respect to x. And allow x to vanish because you supply alpha and x goes away, right? X changes from a of alpha to b of alpha, right? Now, result is, we'll again not get into the proof of this result, but This is a favorite for all examiners whenever they like to set problems on definite integrals. For some reason they like to include this result for solving the problem. But in fact, you would have also seen in problems on limits, a couple of problems where we had to differentiate the integral. We had to differentiate the integral. Now, I dash alpha, which is di d alpha, differentiating I with respect to alpha, will have three terms in it. Will have three terms in it. In the first term, you'll have the integral a as a function of alpha, b as a function of alpha, and you differentiate this with respect to the parameter alpha, keeping x constant. You differentiate this with respect to alpha, keeping x constant. Differentiate this with respect to alpha, keeping x constant. That means partial derivative of f with respect to alpha, keeping x constant. Differentiate this with respect to alpha as if x is. That's the first term in this. In the second term, place this x wherever it appears in this function. Wherever this x appears in this function, replace it by the upper limit of integration. Replace it by the upper limit of the integration, b alpha, comma alpha, and then differentiate b with respect to alpha, and then differentiate b with respect to alpha into db d alpha into db d alpha. That's the second term. That's the second term. In the second term, what have you done? You've replaced this x by the upper limit, which is b alpha, and then differentiated b with respect to alpha. That's the second term. In the third term, which comes with a minus sign, replace this x by the lower limit of integration. Replace this x by the lower limit of integration. Wherever x appears, replace it by the lower limit of integration. And then differentiate a with respect to alpha. And then differentiate a with respect to alpha. Let me illustrate this. Sine of alpha squared x plus alpha cube and the whole thing into x dx. The lower limit a of alpha is sine alpha and b of alpha is tan alpha. Right? You want to differentiate this with respect to alpha. Let me call this I alpha. Let me call this I alpha. Like I said, there will be three terms in it. Be very clear about it. When I differentiate I with respect to alpha, I dashed alpha will have three terms in it. In the first term, the integral sine alpha to tan alpha. And you want to differentiate this with respect to alpha, keeping x constant. So if I differentiate this with respect to alpha, keeping x constant, this x differentiate sine, you get cos alpha squared x plus alpha cube, right? Come down to this. Imagine x to be constant, differentiate this with respect to alpha. So that's going to be like 2 alpha x plus 3 alpha squared dx. Yes or no? That's the first term. That's the first term. Yes or no? In the second term, wherever x comes, replace it by the upper limit and differentiate the upper limit with respect to alpha. So in the second term, sine of alpha squared x replaces x by tan alpha plus alpha cube into x, which is again tan alpha. Wherever x came, replace it by tan alpha into derivative of tan alpha with respect to alpha, that is sec squared alpha. That's the second term. Third term will come with a minus sign. In the third term, replace x wherever it appears by the lower limit of integration and then differentiate sin alpha with respect to alpha. So that means sin alpha squared sin alpha plus alpha cube x sin alpha and then differentiate sin alpha with respect to alpha. That will give me cos alpha. Yes or no? If the lower and upper limits are constants, not depending on alpha, then the second and third terms will vanish. See, if the lower and upper limits are independent of alpha, then the second and third terms will not exist. If this is independent of alpha, depends only on x, then the integral will vanish, because when you differentiate with respect to alpha, it's going to be 0 if this does not contain any alpha in it. And this will be, the integral will not exist, right? So now, say, if I had integral some constant C1 to C2 which does not depend on alpha, some constant C1 to C2 independent of alpha, f of x comma alpha dx, then obviously when I integrate with respect to x, the x I replace by C2, then I replace by C1 and subtract. But the alpha in this will remain. So this whole thing will be of alpha anyway. Now if C1 and C2 are constants independent of alpha, then the second and the third terms will not prevail, So I dashed alpha, in which case differentiate this with respect to alpha, keeping x constant, dx. This would be it. If I had integral fx dx, x changes from say a function of alpha to b a function of alpha, and this is independent of alpha, this is independent of alpha. This whole thing a function of alpha, I alpha. Then I dashed alpha. The integral will not exist, because differentiating this with respect to alpha will give me 0. So then all that I need to do is f of replace x by b alpha and then differentiate b with respect to alpha minus replace this x by a alpha and differentiate A with respect to alpha. I dash. Right? See if I had fx dx, a constant A to x. One thing, this x is not the same as that x. Because see, if this was not x and this was some t, well, it will still give me the same value. Do you realize that? What I mean is, if I had, say, sine x dx, x changes from A to x. I am saying that this x is not the same as this x. Reason being, because if I replace this x by t, then will this integral be any different? Right? But if I replace this x by some t, the integral will be different. So this is only temporary. It's only stopgap, intermediate. Moment you supply the limits, it will be only this x. So one must very clearly understand that this x is different from the x with which you are integrating, with respect to which you are integrating. The x with which you are integrating is only temporary. Is only temporary. Right? Must be properly born. So as beginners, what you might want to imagine is that this is, say, ft dt a to x. This is ft dt a to x. Yes or no? This then would be a function of x. This then would be a function of x. Yes or no? This x. This x. Not this x. Because this vanishes. This goes away. Right? So then if I have to say I dash x. The first term, differentiate this with respect to x, which is 0. Because this t has nothing to do with this x. So differentiating this with respect to x will give me 0. In the second term, replace this t by x. And then differentiate this x with respect to x, which is 1. The third term will be 0 because derivative of a constant with respect to x is going to be 0. So this is very important. Integral ddx of integral a to x fx dx is always going to be fx, is always going to be fx. ddx of a to x fx dx is always going to be fx. Makes sense to all of you? You understand everything here? I want to find the value of this integral. Integral 0 to 1 x power b minus 1 by log x, where b is a parameter. You can look upon b as a parameter. 0 to 1 x power b minus 1. Now when you integrate it with respect to x and supply the limits, it will be a function of b. Will it not be? You integrate that with respect to x and supply the limit, b will stay behind. So it's going to be a function of b. So instead of alpha, my parameter here is b. Let me differentiate it with respect to b. Let me differentiate it with respect to b. Three terms, like I said. In the first term, the integral 0 to 1, and this has to be differentiated with respect to b, keeping x constant. So if I differentiate this with respect to b, x bar b, when I differentiate with respect to b, will give me what? Huh? It will give me x bar b ln x. It will give me x bar b ln x. Right? Now this can be integrated readily. X bar b plus 1 by b plus 1. When I supply the limits, it's going to be 1 by b plus 1, yes or no? X bar b plus 1 by b plus 1 from 0 to 1 is going to be 1 by b plus 1, right? So I dash b is what? Di db. I dash b is di db. I dash b is di db. That's 1 by b plus 1. What am I trying to recover? I. My objective is I. Right? So I get di is db by b plus 1. Di is db by b plus 1. Integrate. I get I equal to log b plus 1 plus a constant of integration. Yes or no? Right? Do you realize I need to find c, the constant of integration, because it's a definite integral. I need to find c, the constant here. I is log b plus 1 plus c. Realize that I at b equal to 0 will be 0. If you plug in b equal to 0, do you realize that I will become 0? So, when b is 0 from the mother integral, I get I as 0. So, plug in b equal to 0. If you plug in b equal to 0, I turns out to be 0. So, 0 equals log 1 plus c. So, c is 0. So, c is 0. I then turns out to be log b plus 1. I then turns out to be log b plus 1. You know what I'm saying? This is log b plus 1. Now, one thing I have to tell you. You know, again, this is childish mentality. Some of you, what you do is when you give me integrals, you remove this 0 and 1. This function does not have a primitive. X bar b minus 1 by log x doesn't have a primitive, but the definite integral exists. You can't find a function which on differentiation gives me this. But the definite integral exists and is log b plus 1. And you tell me you've seen it in a book. So, now, let me give you more of this. Say greater than 0, e power minus alpha x sin beta x by x dx alpha, let's say, is a fixed positive number and beta is a parameter, and say beta is a parameter. So when I integrate it and supply the limits of integration, this whole thing will turn out to be a function of beta. It will turn out to be a function of beta. Let me differentiate this with respect to beta. Let me differentiate this with respect to beta. I dash beta then. Three terms in it. The first term is the integral. And this has to be differentiated with respect to beta, keeping x constant. keeping it constant, right? So e power minus alpha x cos beta x, and then beta x with respect to beta is going to be x. Is going to be x divided by x dx. Yes or no? Cos beta x is real part of e power I beta x. Is the real part of e power I beta x. Cos beta x is the real part of e power I beta x. Is the real part of this, which then is real part of 0 to infinity e power minus x into alpha minus I beta dx. E power minus x into alpha minus I beta e power mx by n. So this will then turn out to be, this is all I dash beta which then will turn out to be real part of e power minus x into alpha minus I beta, right? E power mx by n by minus alpha minus I beta. X changes from 0 to infinity, right? When x is infinity, this will be 0. When x is 0, this will be 1. This will be 1. So this would become 0 minus 1 by minus alpha minus I beta. Yes or no? Which would be real part of 1 by alpha minus I beta, real part of 1 by alpha minus I beta, right? No? Which is real part of alpha by alpha squared plus beta squared, multiplying by alpha plus I beta, which is alpha by alpha squared plus beta squared, alpha plus I beta, alpha plus I beta. So this is going to be alpha by alpha squared plus beta squared, right? Now that's I dash beta, and I'm intending to liberate I beta from there, right? I dash beta from all this turns out to be, I dash beta means di d beta alpha squared plus beta squared. Gi then turns out to be alpha by alpha squared plus beta squared d beta, right? Integrate. When I integrate this, I get alpha comes out 1 by alpha tan inverse beta by alpha. So this is simply tan inverse beta by alpha plus a constant of integration plus c. That's the I, a function of beta. Yes or no? Right? Now, very clearly, if you plug in beta equal to 0, I will become 0. That means I at beta equal to 0 is 0. I at beta equal to 0 is 0. So if beta equal to 0, I turns out to be 0, right? I is 0 when beta is 0. So I is 0 when beta is 0 means tan inverse 0. That means C must be 0. C must be 0. Right? No? which means this integral turns out to be tan inverse beta by alpha. And again, let me tell you, if you remove these limits of integration, no power on earth can integrate this function. It does not have a primitive. And yet you do this. You remove you strip it of the limit, and you say, sir, I saw it in a book. Please integrate this function. Get the book. Okay. 0 to infinity tan inverse beta by alpha. Now, realize that when alpha tends to 0, this limit, this integral becomes sine beta x by x dx 0 to infinity. Right? When alpha is 0, this will become sine beta x by x. Now when alpha tends to 0 here, this is like beta by something coming closer and closer to 0. Now if beta is positive, this will be plus pi by 2. But if beta is negative, this will be minus pi by 2. Yes or no? So very clearly this will be pi by 2 when beta is positive, see? And will be minus pi by 2 when beta is negative. Integral sine beta x by x changes from 0 to infinity, is going to be plus pi by 2 when beta is positive, is going to be minus pi by 2 when beta is negative. Obviously, see, if you change the sign of beta here, a minus sign will appear here, and it will become negative automatically. Again, you strip these limits, integral sine beta x by x cannot be formed. Definite integral exists. Right? This result, of course, the last one, integral sine beta x by x, 0 to infinity is plus pi by 2 when beta positive, minus pi by 2 when beta. You must remember. In fact, sine 2x cos x by x 0 to infinity. This could be written as half 0 to infinity sine a plus b plus sine a minus b, sine 3x by x plus sine x by x, sine beta x by x 0 to infinity pi by 2 plus pi by 2 pi. This will be pi by 2. Got me? Because this will be pi by 2, this will be pi by 2. So pi by 2. Got me? Say m is a natural number. And a is positive. X power m e power minus ax dx. I want to find this. X power m e power minus ax. What I do is, I just look at e power minus ax. 0 to infinity. Very clearly, e power minus ax is going to be e power minus ax by minus a 0 to infinity, which will be 1 by a, because at x equal to infinity, this will be 0. At x equal to 0, it will be 1. 0 minus 1 by minus a. So 1 by a. Yes or no? No. Minus ax dx is 1 by a. 0. Treat a as a parameter. Treat a as a parameter. Treat a as a parameter. Differentiate this with respect to a keeping x constant. Differentiate both sides with respect to a keeping x constant. So when I differentiate this with respect to a keeping x constant, there will be 3 terms in it. In the first term, I'll differentiate this with respect to a keeping x constant. The second and the third terms will be 0 because the lower and upper limits are constant. So the first term, if I differentiate this with respect to a keeping x constant, it's going to give me minus x e power minus ax. Yes or no? It's going to give me minus x e power minus ax. And that's going to be minus 1 by a squared from right hand side. Yes or no? Right? Minus. Hey, differentiate again with respect to a keeping x constant. Differentiate again with respect to a keeping x constant. So you will again get 0 to infinity. You will have a minus x here, minus 2 by a cubed here. So you will have minus x again coming here, means you will have x squared e power minus ax dx. 2 by a cube. Differentiate again. Differentiate again, you will get x cube. This will become a power 4, 3 factorial by a power 4. If you differentiate another time, x power 4, etc., 4 factorial by a power 5. Yes or no? And if you keep going like this, then eventually, inductively, you right. You would end up getting, if you differentiated m times, if you differentiated x, you will get like of x power m e power minus ax 0 to infinity equals m factorial by a power m plus 1. Integral 0 to pi by 2 ln 1 plus y sine square x. Integrate with respect to x and plug in the limit. X goes away, but y remains. It's going to be a function of y. It's going to be a function of y. Differentiate with respect to y. Right? I dashed y. Three terms in it. The second and the third terms would be 0 because the lower and upper limits are constant. Differentiate this with respect to y, keeping. So then you get 1 by 1 plus y sine square x. Differentiate this with respect to y, so you will have a sine squared x. And there is also a sine squared x here. Yes or no? That means I need to integrate this with respect to x. Simpler looking thing now. Multiply numerator denominator with sec squared x. If you multiply numerator and denominator with sec squared x, then sec squared x dx d of tan x, and then sec squared x I write as 1 plus tan squared x plus y tan squared x. X changes from 0 to pi by 2. Right? I write as 0 to pi by 2. See, this I could write as 1 plus y tan squared x plus 1, 1 plus y tan squared x plus 1, and I can take 1 plus y common from this. Yes or no? I could do this. So dt by t squared plus a squared, 1 by a tan inverse t by a. Yes or no? dt by t squared plus a squared, 1 by a tan inverse t by a, where a is 1 by root y plus 1. No? Root 1 plus y tan inverse tan x into root y plus 1, where just rewrite it somewhere else. I dashed y is 1 by 1 plus y root 1 plus y tan inverse root 1 plus y tan x. X changes from 0 to pi by 2. Yes or no? X changes from 0 to pi by 2. Clear? When x is pi by 2, tan x becomes very large. So this becomes very large, and tan inverse very large is pi by 2. When x is 0, this is 0, tan inverse 0 is 0. So this will become pi by 2, this will simply become pi by 2, and this will be 1 by root 1 plus y, 1 by root 1 plus y. Yes or no? Now, once I dashed y in place, write this off. I dashed y is pi by 2, y plus 1 to power minus half. Right? So di dy, this is di dy. So di then is pi by 2, y plus 1 to power minus half dy. Yes or no? Integrate. So I then is pi by 2. Hey, this is function raised to a certain power into the derivative of the function. So this is going to be y plus 1 to power half divided by half. That half will cancel this. Plus constant of integration. So I then becomes pi root y plus 1 plus c. We need to find c now. Right? Very clearly, when y is 0, this will become log 1. So I 0 is 0. I at y equal to 0 is 0. From the mother integral, if you plug in y equal to 0, this will become log 1. So I at y equal to 0 is 0. So if I at y equal to 0, then very clearly c will then become equal to minus pi. See, y is 0, I is 0, then pi. C then will become minus pi. Therefore, I then is pi y plus 1 to power half minus pi. And if you again try to bleed it of its limits and integrate this, God bless you.